So I'm going to tell you about a calculation testing the S-duality conjectures in N equals 4 super Yang-Mills theory, which are old and very well tested, if you like, by other means. This started as a sort of a warm-up, an easy warm-up for application to questions having to do with theories with less supersymmetry. But it turned out that this calculation is already turned unexpectedly complicated. So I will tell you about it. First of all, I'm going to spend a bit of time just reminding you what S-duality is and what the S-duality predictions or conjectures are for N equals 4 super Yang-Mills, and then very briefly tell you about what the computational challenges are in our test, and then end with an interesting possible refinement of S-duality. So what is S-duality, first of all? So S-duality refers to the exact equivalence of two different field theories. So what do we mean by that? Well, something psychological. It's you thought that they were different theories and they turn out to be the same. So I'd like to describe this in a more intrinsic way. So let me motivate it as follows. A familiar example of something like this are universality classes, where we have two different microscopic descriptions and their equivalent in the infrared. So S-duality is not this kind of equivalence, which is sort of equivalence at the endpoints of RG flows, but we would like to say that we have instead, let's start with two different free quantum field theories, and let's say there are some couplings that we can turn on. And then the question of S-duality is, are these two theories connected? That is to say, we thought they were separate theories, but it may be that in their space of couplings, they form one continuous connected space. So that's the intrinsic notion of S-duality. Two quantum field theories, and let's again say start with free quantum field theories, are S-dual if they can be connected continuously in their space of couplings. Okay. So from this point of view, S-duality is just defined as the geometry of spaces of continuously connected families. The predictions of S-duality are, what are these funny manifolds that are called M here? And what are their shape, what's their geometry, and so forth. And the cleanest setting for this study are in families of conformal field theories, in which case M is then the space of exactly marginal couplings, also known as the conformal manifold. So this is really, I'm going to rephrase S-duality conjectures as a statement about what are the conformal manifolds of a set of theories. So I'm going to give an example, and this is called electric magnetic duality, and it's generally not thought of as S-duality, but because it's a free theory. It's just free Maxwell theory, and we're going to look at its couplings to non-dynamical charge sources, electric and magnetic charges. So we combine those in tau as usual, and then you're probably all familiar with this. Then you find that there are a set of equivalences on these couplings to these sources generated by these two guys. And in the space of these complex couplings, there is a fundamental domain under the group generated by these equivalences, which is just this blue region here with their edges identified. So this blue space, that is this in this particular example, that's this space M, this analog of a conformal manifold for this case. The group is the modular group, SL2Z, and this is called the electric magnetic duality group. And this space, let's look at it for just a second. If you identify its edges, it's more or less something like a sphere with 3 marked points, kind of a cusp with as imaginary part of tau goes to infinity, and then a Z2 sort of orbifold point at tau equals I, and a Z3 orbifold at these 2 identified points. So in terms of a geometry, we could say that the electric magnetic duality is the statement that this space M is topologically a sphere with these 3 marked points with these certain properties. And in fact, if I give you such a space, if I can recover the duality group from this geometry. In this case, it's the statement that the fundamental group of this space in the orbifold sense is, as an abstract group, this group. So this is just a statement, just to get you used to this idea of thinking about S-dualities in these geometric terms. So, but the term S-duality is generally reserved for interacting conformal field theories, not discrete thing. Okay.
It was possible to say that in certain sense it's kind of extended notion of field definition, because say we have this we can use electric potential or magnetic potential, but maybe not local, whatever, but there is some kind of
in the free field case that I just talked about, yeah, you can certainly understand it in terms of field redefinitions,
Yeah.
like you said. And field redefinitions are just a way of re-expressing your theory so that it's the same theory. And that's the way we understand completely electric magnetic duality. But in a strongly interacting gauge theory, we don't have these tools at our disposal. So it becomes a difficult problem to actually figure out what is the shape of the conformal manifold of, say, n equals 4 super Yang-Mills theory or other theories with
even in this direct case, you can say that you have kind of either different description using different kind of potential, but
I think the place where we understand different descriptions are not in the strongly coupled or interacting gauge theory itself, but if we look at the low energy effective actions out on the moduli space, that's when we have this thing, and that's precisely the test that I'm going to perform. I'm going to look in the low energy theory, as I'll mention in just a minute, and then ask, does the equivalence of the low energy theories match the predicted equivalence from these S-duality conjectures? It's not quite as trivial as it may seem. So here is, just to remind you, here then equals 4 super Yang-Mills. The point is, the basic properties is that it's a conformal field theory, and it has a single complex exactly marginal coupling, again called tau. And we want to understand for a given such theory, what is this space of couplings? At least naively, this Lagrangian that I wrote was specified by specifying a Lie algebra, a simple Lie algebra. The other thing that these theories have are a moduli space of vacua, on which, at least at generic points, the gauge algebra is Higgs down to a bunch of U1 factors. So at low energies, it looks like some number of copies of electromagnetism. So this is called a Coulomb branch or phase of the theory. And it's this fact the existence of this moduli space of vacua that we're going to be taking advantage of. To learn something or about the possible shapes of these conformal manifolds. So there's a long history of S-duality conjectures, successive refinements until about 10 or whatever this is, 12 years ago, in this reading between the lines paper of Aharoni, Seiberg, and Tachikawa, when the most kind of a final form, if you like, for the S-duality conjectures for the n equals 4 super Yang-Mills theory were finally understood. They differ qualitatively from kind of the original early kind of naive versions of S-duality. Just in case you're curious. And their final answer is that for each gauge algebra, there are many possible global structures or global forms of the theory, labeled by an actual global form of the gauge group. Remember, for each simple Lie algebra, there can be many corresponding gauge groups, compact gauge groups. And in addition, there are some additional discrete labels, which they call discrete theta angles, and they figured all these out and labeled them. I'm not going to go into that here. For each global form, there is a marginal coupling, and so there is a corresponding conformal manifold. And S-duality says how these conformal manifolds are connected to one another, how they. So let me just in case you haven't seen this before, just give you some examples. The simplest example would be SU2, in which case there are 3 of these global structures. There's 2 global forms of the SU2 Lie group, SU2 and SO3, and the SO3 has 2 of these, has this discrete theta angle. So there are 3 global structures, and it turns out that they're combined together into one single connected conformal manifold, and it's just 3 copies of the fundamental domain of that PSL2Z acting on the upper half plane. It's the one that I had written before here in the electric magnetic duality case, and another copy for the other SO3 structure, and yet another copy for the SU2 structure. And if you combine all of this thing with the edges identified appropriately, so this whole thing turns out to be a space, which is, again, has the topology of a sphere. It has 2 cusps, 2 weak coupling cusps, an SU2 weak coupling cusp and an SO3 cusp. And there's a special point, a Z2 orbital point at this strong coupling back here. This is the prediction or if you like, conjecture for what the S-duality of the SU2 n equals 4 theory is. And in general, let me just point out very quickly. How much time do I have? Okay. Oops. Yeah, that was interesting. For let's say the SUN case, depending on what n is, there can be more than one disconnected component of the conformal manifold. The number is given by the number of square divisors of the number n. And these different disconnected components are called in the literature S-duality orbits. So I want to know the number of S-duality orbits and the geometry of each S-duality orbit. So here's some examples. For instance, I've given this example of SU6. There's only one square divisor of 6, namely 1 square divides 6. So there's only a single orbit, and it's just a sphere with 4 punctures. All of them are cusps corresponding to the different global forms of the gauge group, and you can work out what the S-duality group is, and it's a certain modular subgroup. And I just pointed this one out because that one is an example which contradicts prediction, if you like, that Goddard, Moitz and Olive for some uh, and successors put forward in the early days of this whole game. Here are some other examples. I'm not really going to spend much time on them. But for example, SU8 has two square divisors, 1 squared and 2 squared divided 8. So it has two disconnected components. Here are their geometries. This one, for instance, here's an example where the conformal manifold for this component happens to be equal to a conformal manifold for a different theory, just as an abstract Kähler variety, but nevertheless, they correspond to distinct theories. Here, just for fun, here's the first example, turns out SU11, in which M has not the topology of a sphere, but it turns out to have genus 1. Okay, good. So all of this was just a review of S-duality conjectures for n equals 4 supernomials. So what do we do? Well, as I mentioned, there is this moduli space of vacua, and we can compute exactly the low energy effective action on this moduli space, following Seiberg and Witten. And this gives a very information-rich exact observable that we compute in these theories. And so we can simply ask, S-duality tells us that the inequivalent n equals 4 theories come in this class of conformal, are labeled by these conformal manifolds. Do we see the same thing for their low energy effective actions? So what is, I'm not going to go into details here, but you want to understand, okay, how do we figure out what these low energy effective actions are? They're encoded in a geometry of this moduli space called a special Kähler geometry. And I'm not exactly going to define what that is now, but I will remind you or tell you that the Kähler geometry of these n equals 4 theories has been known for a long time. It's simply a flat a vector space orbifolded by a finite discrete group, the Weil group of the gauge algebra. This is some simple geometry, and it clearly has nothing to do with all those global structures that were predicted by to govern the conformal manifolds by Aharoni, Seiberg, and Tachikawa. So this seems like a very coarse invariant. But the problem with this description is that only captures the Kähler geometry and not the special Kähler structure. And each of these Kähler geometries admits potentially many different inequivalent special Kähler structures. And that's what we, myself and my collaborators, have done, is actually figured out this math problem of classifying the special Kähler structures compatible with a given Kähler structure, Kähler orbifold like this. And the answer, mathematically, it turns out that the answer is that they're classified by integrally inequivalent representations of the Weil group into the symplectic group over the integers. Okay, so we just have to solve this math problem, and then we find in this way the set of Kähler structures of this low energy, these Coulomb branch effective theories. to give you an idea, so it turns out this problem had not been solved, even though uh, um, integral representations of the Weil group is something that's actually been pretty well studied in the math literature. This particular problem hasn't been, and the reason is that these representations are necessarily not irreducible. And we then have to classify the reducible but indecomposable representations like this. So this hadn't been done. We took us a little while, but we finally learned enough math to figure out how to do this. And I should say who we is myself and Antoine Bourget, Julius Grimminger, Matteo Lotito, and Mitch Weaver. And this should be out soon. To give you an idea of what the special Kähler structure is, we said that at low energies, the theory looks like, let's say, R copies of U1 electromagnetism on the Coulomb branch. So there is an R by R matrix of complex low energy electromagnetic couplings. And these infrared couplings, this matrix of couplings, of course, can in principle depend on what the UV coupling is, the microscopic coupling of the N=4 super Yang-Mills theory. So these guys are, as I change the UV coupling, these guys are going to trace out a one-dimensional subvariety of the space of these matrices, modulo low energy electric magnetic duality. So from the point of view of learning about the SK structures, we'll see them as being a set of orbits in this much larger dimensional space, one-dimensional complex curves. And the expectation is, the question is, we now know how to compute these things. Once we compute them, do they match to the curves predicted by S-duality? They should be complex curves. They actually inherit Kähler geometry. Do they match at the level of having the same Kähler geometry, not just their number, and so forth? So that's our question. Here are our results now. Well, first of all, they do match. They are at least in number, they're in one-to-one correspondence with the S-duality orbits proposed by Aharoni, Seiberg, and Tachikawa. There are a few cases where a given theory with a given gauge algebra has two different predicted components, which are equivalent as Kähler manifolds. So you would say, oh, there should be two S-duality orbits, but you can't tell them apart. They look identical, and we can tell them apart because we see, oh, we have two identical looking orbits, but they live at different locations in this larger space, so we can tell them apart. We can see that they're this low energy observable, their tau ij's are indeed different. So that's nice. There are, kind of conversely though, there are a few cases in which our SK structures do not quite distinguish between different theories. And so here is I'm just flashing up a list of our results. The one in red are the cases where we get everything on the nose except for these cases in the so-called BC theories. Those would be the SO odd SP gauge algebras. In particular, just one of each of their S-duality orbits, we find a larger kind of set of identifications in the infrared than are proposed in the ultraviolet. Well, this is not actually a contradiction. There's no reason in principle that an infrared observable necessarily distinguishes between different theories. But since S-duality is just a conjecture, we could ask, well, maybe we should take this as evidence that that there's extra S-duality identifications. Well, this can't be the case for what I just said, because you can look and they would actually identify two different weakly coupled theories, and there are other observables that we can use to distinguish them. However, and here's one thing that we've noticed, there's at least one pair of strongly coupled N=4 super Yang-Mills theories, which have identical SK structures just at strong coupling. And here's the example. In the theory with SO5, which is the same thing as SP4 gauge algebra, it turns out that the S-duality prediction is that there are two S-duality orbits. They have some different shapes. And so it's just this sort of two different connected classes of this theory. This is the lowest rank at which you get these two different connected classes. But if we look at their SK structures, it turns out that there is just one sort of kind of special, but otherwise random looking point on these two manifolds where the SK structures actually coincide. And so a speculation is, could it be that instead of two separate classes of theories, that at somewhere deep in strong coupling, these two classes of theories are intersect one another. Those two red dots are actually the same theory. And it's kind of interesting to think about what would be the properties of an N=4 theory at strong coupling that would have this kind of intersection of its conformal manifold or self-intersection. Anyway, that's a conjecture. We can't find anything wrong with it, but we can't find any additional evidence for it either. And let me just finish with some open questions. In general, this question, I gave this one example, so how about other examples? Well, it turns out it's very hard to answer this question just mathematically, because generally the low energy tau ij couplings at these 2 points look quite different. And it was just that there happened to be an SP4Z transformation which took one to the other, so it said they were equivalent. But searching in the space of SP2RZ, these integral transformations on this Siegel upper half space is very computationally difficult. So we have not been able to answer this question in general, or even at rank, say, 3. And then there's other questions about analogs of all of these questions with less supersymmetry. So, thanks.
Questions? So thank you for my understanding is that when you have this modular space, it is kind of each module corresponds to like different physics reality, right? It's kind of, I would say that in a different series, each module comes with different physical laws.
When you're saying moduli space, you mean the conformal manifold, the different values of the.
No, just generically, that you have some number of series, and then taking the particular model, you're choosing this particular series you consider, right?
Okay.
So when you're talking about this space, you're talking about in this way, it's a space of series.
Yes, exactly.
Right? It's not like, how to say, it's they're not each one is a different physics, right? But how they connected, right?
Right, exactly.
Right. So in this sense, no, with this special color, it's like a special points in this kind of modular space, or how to understand this special color to the case.
I mean, for each point in the conformal manifold, that's at least conjecturally separate N=4 super Yang-Mills theory. Each one has a moduli space of vacua, and I can compute its special Kähler structure. It's a property of each of these things. It varies in some subtle way as you move around in these conformal manifolds. And that's what we've computed. And so we've looked at the classes of special Kähler
Yeah.
manifolds of this sort, which we can, we can solve for mathematically, and just ask whether they fall into the same classes as predicted by the S-duality conjectures.
Yeah, but
And
it is still different series in the same sense as you told before.
Well, if the low energy observable, the special Kähler structures are different, they are definitely different theories. There's no way one theory can have two different predictions in the infrared. But it's possible that these special Kähler structures can't differentiate two different theories in the ultraviolet. It may just happen to have the same infrared. And there's a few cases of that.
So we need to find S-duality, it's like a necessary assumption, is there's a formal
It's not a necessary assumption. One trivial thing is you can take n equals 3 theories and you have some definition of them, some construction of them. They do not admit exactly marginal operators, and then their conformal manifolds are just points. But for a given set of data that people now think is enough from various constructions to define n equals 3 theory, we can show that, oh no, there actually exists viewpoints for 4 points instead. So you would say, oh, you were mistaken. It actually has its conformal manifold instead of being 1 point is 3 points.
When we say one possible, there's no specific example. It's very hard to find the whole manifold from.
In non-SUSY theories,
It's very hard, right? But if you have this keep working on this,
you can imagine that, and yeah, we can talk about it, but
let's talk about it.
you can apply this to whole quantum field theories in principle, so.
Let's talk.
One last quick question, so again, so I can try to understand the intersection.
Yeah.
The marginal operators is shaded with the two.
Yeah.
So, but then this intersection would mean that this several marginal operators are mutually non-local somehow, if you cannot go
Yeah.
in between.
I mean, mutually non-local would just mean that there's in some sense two separate marginal operators, but I'm not allowed to turn both of them on at once. In other words, there is a constraint saying, like, if I call the marginal operators tau 1 and tau 2, there's a constraint that tau 1 times tau 2 has to be equal to 0. So I can only turn one or the other
It's not
on.
necessarily that they're mutually non-local, but there's
Yes, a constraint, yeah. This is speculation because we don't actually, it's a little hard to see if that breaks any rule.
Some of them both would one of them become no longer marginal. So, yeah, the other way of thinking about that.
That would be the way.
maybe in the interest of time, we can take further question at the coffee break and can please again.